So Nong, the floor is yours.
Thank you very much for okay. So I guess you see my full screen, right?
Yes.
But let's test as we test before if it's work correctly. So you see my note or deep note?
Yes.
Okay, perfect. So now I show my slides. That's perfect. Okay. Now, actually, I already got the introductions of myself, but maybe I should also introduce myself again. Yes, I am Nongnuch Artrith. I just moved to Utrecht a few months ago. So my tutorials talk or my introductions today, I will mainly discuss about developments or construct artificial neural network potentials for materials. So as the introduction, so I also would like to also thank the organizers and also the Psi-k network for organizing this really very nice workshop, because this is really my field, because I really did my PhD on these topics. It's really very nice to invite like the next generations of young scientists to join and really to learn and work together, or even maybe think what to develop further in the future. So yeah, I cannot talk about everything, but I will mainly discuss and talk about my own work related to the development of neural network potentials that use our machine learning framework, the atomic energy networks or AENet, which I will demonstrate a few examples of the complex materials. And most of our models and also database after we develop, we always share with the scientific community here. So actually, this is already this conference, but just to brief and give overview, the general idea of machine learning potentials is to use machine learning methods for representing the potential energy surface, or PES, from a very accurate energy methods, for example, first principles, quantum mechanics, or density functional theories, or DFT. So I use this as like a QM or quantum mechanics database. And then we use machine learning models to interpolate, or for the interpolations to construct continuous, efficient and accurate machine learning potentials. And then we use it in applications, for example, in applications that if we have the accurate energies in larger scale Monte Carlo simulations, if we have really accurate forces, we can also use in the molecular dynamics simulations. So our approach, we use artificial neural networks for the interpolations, because they can be really very accurate and can be trained on large data sets with hundreds of thousands or even millions of data points. And the models only need atomic positions and are reactive and full dimensional. But of course, it takes a bit of effort to construct and also to validate them before we really can use it to our own applications. I know that in the introductions already, the organizer already show very nicely how the developments of machine learning potentials, but now I would like to focus only on my own research that I have been involved on the developments of artificial neural network potentials for some time. But actually the idea to use neural networks to represent potential energy surface is not new. As you can see here already in 1995, Dorrant already showed in JCP to show that the first potential energy surface to represent complex system with neural network, for example, nickel 1011 and CO molecules. And then 2004, Scheffler group discussed in chemical physics letters to looking at the potential energy surface based on neural networks on palladium 100 and also potassium and hydrogen molecules. It's really very complicated, right? But they developed and fitted only specified for this system. But for the first time that in 2007, Baylor and Palinello, I think most of people in this room know very well that this is the first time to use high-dimensional neural network potentials for any number of atoms, but they discuss complex crystal structures, many different types of crystal structures, but only describe single chemical species, only silicon. And then when I joined the Professor Baylor group, Together with also the colleagues, Tobias Molowitz, we extend the methods to multi-component systems and also include electrostatics. And we demonstrate the capabilities of neural potential with zinc oxide that also describe the charge transfer in the system. But then 2017, for multi-component system based on Baylor-Palinello system that we discussed is not enough to describe real complex systems that I work with the Professor Sedas. The battery system have many different chemical species. So we extended the methods for example, we can describe even 11 chemical species. And actually there are many more since 2011 show the developments on the neural network models. And you also can see here in 2017, Roydbeck and also the group shared the annual force field and with large data set like 5 million data points and can explain and describe really nice organic molecules. So as you can see that the progress or the number of publications since 2011, neural network potential publication increasing really very many. But this is I only show and type only neural network potentials in Google Scholars. But if we're looking at more keywords, because in the last few years, like machine learning force fields or machine learning potentials, and there are many, so you can see that the number of publications really increasing, but still not many models can be used. This means the field still need to continue to develop together. This is just an example of a simple feed-forward neural network. So on the left-hand side, this neural network has 3 layers with artificial neurons or nodes. So input layer, hidden layer, and output layer. For our application, the input layer describes atomic structures, and the output layer is the energies of the structures. The number of nodes is 1. Actually, this is only 1 or more hidden layers determine the model complexities. And the equation here is on the right-hand side. You can see that this corresponds to the same 3 layers neural networks on the left-hand side. And the atomic forces can be calculated from the analytical derivatives. In this equation, so each node or artificial neurons of the neural network apply a nonlinear activation functions like you can see here. This is just an example of hyperbolic tangents. So just to make it as a practical, like you can see here, we are fitting a nonlinear parabola curve. Like you can see here, the black diamond shapes. So I have the 2 terms, like you can see here, the blue. This is the curve that we have, the one hyperbolic tangent, and the green one, this is the second one. When we combine this blue and green together, and then sum up with bias or the constants that is also can shift the neural network potential to the right reference data of the parabolas. So this is how neural network fittings in very simple mathematics here. But in realistic, we have very complicated. This diagram show high-dimensional neural networks. So now in materials, like we have, this is the total energies. So each the total energies come from the sum of the atomic neural network energies, like you can see here. And each atomic neural network atomic energies come from the atomic neural network, like I just showed in the previous slides, and then come it here. But you can see here the atomic positions like a Cartesian coordinate. We transform to a local environment, which we call fingerprint, which is like a set of many body functions that describe local environment of each atom. So usually the system that I'm involved or I'm interested in, this is like condensed materials that we use a radius cutoff around 6 to 8 angstrom. And this is developed and described this method by Baylor-Palinello. More details, you can also read these papers. So actually, our work, we only use neural networks to describe or interpolate our machine learning models. But the most important that I would like to point is out also the descriptors or the input node, which is also very important. For example, here, just give overview as an introduction. So the descriptor has to follow the invariance of energies. For example, here in these equations, the properties of the atomic energies, the total energies of structures, sigma, is the sum of atomic energies, right? And the atomic energies have to follow the physical invariance of total energies. And the atomic energies have to be invariant with respect to exchange of equivalent atoms, and also with respect to translation and rotation of structures, like you can see here. And additionally, descriptor needs to have also constant length, and each neural network has one specific numbers of input nodes. So therefore, the length of the atomic structure descriptor has to be constant. The size of the descriptor has also to be independent of number of atoms and chemical species. So important chemical species in the structures. So this is what we want. That's why I made the wish list of the input or the descriptors that are really important. We made a list of the requirement of the ideal or the dream of descriptors. For example, the descriptor should be automatically and should not require many tunable parameters. Its accuracy should be systematically improvable. It should be as efficient as possible, and its computational cost should not depend on number of chemical species. So we discussed this and we implemented in also our atomic energy network code, or AENet, and more detail you can read in these two papers. Just in brief, I like to draw it as a cartoon, like you can see here. The descriptors of our local atomic environments. So the fingerprint or descriptor used by our AENet potentials is based on an expansion of the local radial distribution functions, or RDF here, and angular distribution functions, or ADF here, in the basis sets of Chebyshev polynomials. So here, Psi alpha is the Chebyshev polynomials of order alpha. And C is the coefficient, like C alpha is the corresponding expansion coefficients. The local atomic structures here, A and C, this is the local atomic structures with the coordinate or coordinate of all atoms within a radius cutoff RCs, which is described by two sets of coefficients. So one for bond length, this is the RDF, and one for bond angle, this is the ADF. And this is the first set of our descriptors. And now how to describe many chemical species. So we introduce a second set of weight coefficients. It's used to capture the local atomic compositions or atomic types. So I use T here, or chemical species. And you can see here W's, and many W's is also to describe many different chemical species. For example, here in our case, the W's that we introduce, if you have one chemical species, the weight or WT is 0. If you have two chemical species, the W can be -1 and +1. If you have 5 chemical species, our WT can be like a -2, -1, 0, +1, and +2, for example. This is just to help to classify that you have many different type chemical species. Maybe I'll show the cartoon, it's not that easy to understand. I also briefly show as equations, maybe it is easier to understand. And this is, I just show that we have the description or descriptor of the RDF, and then introduce different type of chemical species by introduce species dependent weights here, and also here for the ADF. And this is the set of the expansion coefficient that we have. So this means our descriptors contain two sets of the descriptors. The first set is to describe atomic structures, and then the second set to describe atomic types. Okay, and we also show and this benchmark for a different type of structures and different type of chemical species. Like you can see here together with the Sader groups. So we test our descriptors, for example, in x-axis here, this is the number of dimensions. And this is the root mean square errors compared between the DFT and our neural network predictions. You can see that this is the crystal structures. And on the right-hand side, this is we also have a test with the amino acids complex, which is around 11 chemical species. So you can see that most of them all different chemical species have really low or MSE is around 3 millieV per atom. So this is example of the neural network fitting is really very simple. The first example, this is water dimer. And the second example, this is complex copper gold alloys. The black diamond shape is the reference data, and the solid line, as you can see here, also on the right-hand side, showed neural network fittings. So after a few iterations of training, our neural potentials can really represent reference data accurately, like you can see here. So this means neural network can really establish a functional relationship between the structures and its energies. Now, not only train and fit with the energies, we also develop another, how to say, further that we also include atomic forces in the training sets, but including the real or forces is quite expensive. So together with April and Professor Keisner from Stuttgart, so we include atomic forces via Taylor expansions. Just in brief, you can see here neural network potential. Usually you need a lot of database, right? But sometimes we cannot generate and develop large database so easily. But we have sometimes quite small data set. How can we make use of small data set and then make good neural potential directly? So together with April, we introduced new methods, but just want to show you and demonstrate how what I just mentioned here. The x-axis, this is the error in absolute forces. And this is the frequencies, how the forces happen. When you have small number of structures, you can see that the forces quite a large errors, but we have more data points, the forces in the error and forces is quite small. And also the same, we're looking at the mean absolute errors. When you have many data points, you can see that the forces is quite accurate. But how can we use small data set and then also improve the force accuracies? So what we did is that here you can see we introduce include force as approximate energies via Taylor expansions, like introduce some small atomic displacements or distances, each actual DFT calculations, and then introduce it, include more in the data set. Maybe I can show you one simple example. This is a carbon dimer. In the blue dot, is it the sample or let's say reference or DFT reference energies, for example. And then the target, this is a gray color. After we use these 7 data points train neural potentials, you can see that sometimes even the fit very well, but we can predict wrong atomic structures and also wrong energies. But we introduce our methods, use more informations by introduce small atomic displacements and then include force information from Taylor expansion. You can see that we introduce more data points. In this case, we introduce like a plus X minus X in this dimer. And we have more data points included in the trainings. And then we fit again. So you can see that neural networks potentials from using the Taylor expansion here improve and predict correctly atomic structure or distances and also get accurate energies. So we test a few examples, but this is one cases we have 6 water molecules in the structures, and we also try many different random atomic displacements. For example, in this case, start from 0.01 angstrom, 0.02 angstrom, and this is to check the mean absolute errors of the forces. You can see that for water system, increasing or introduce random atomic displacements around 0.01 give a good or very accurate forces. But if you increase very large distances, you can see that it's also quite give quite not good information of the force errors. But this means each system we need to test and also find the right displacement include to your training set. But the question is that how can compare with the direct force fittings that we have here, right? You can see that this is the direct force training with the black curve here. This is really very accurate, use all informations. And then we use our methods, random displacements in blue. It's also quite good. It's better than just use the pure only energies training only. But when we compare the CPU time from these 6 water molecules, so it takes 8 times more computed CPU time than the Taylor expansion methods. So if you are working on molecular systems, maybe this is doable, but typically my complex system, I'm working on like a condensed or periodic condensed structures. Direct force trainings with all forces components is really very expensive and not really easy to get all information. So for example, I show in this case, this is the lithium cathodes. Battery materials contain 5 chemical species. So we cannot use all atomic forces and many different structures in the training set. So we use the Taylor expansion methods. It already show a good performance. And we demonstrate here using the 800 DFT reference data of this complex 5 chemical species of the cathode, lithium, the cathode materials here. And looking at the trainings, only use energy training only, and we try many different fits, and we take each neural network fittings and then run MD simulation. You can see the MD1 in the yellow. We try even a long time MD simulation at 1 nanosecond. It's not really equilibrate and it's fluctuate very much. And the second one, this is only energy training with the 800 DFT structures. It's already explored very early. But then when we use our force informations via Taylor expansion, it helps us and make MD simulation is more stable. So this already showed that our method, Taylor expansion, is also help and improve our neural potentials. But note that this 800 reference data not general neural potential, but this is just to demonstrate. But for real application, we need to include many more structures. So this is all of the steps, how we construct machine learning potentials in practice. So we generate a large DFT or even initial small DFT database first, and we do iterative refinements until we really get a good or accurate neural potentials that you can use in your own applications. Many times that we always get not really good potential directly, we have to really validate and test. But we also include the active learning methods to help and to find what structures not really cover our full potential energy surface. And this is we have to do iterative refinements. We also show some example of the Jupyter notebooks, how to demonstrate this diagram via this GitHub link. So everything that I just discussed in the previous slides, we implemented in our open free software package, the Atomic Energy Network. This is the link to the website and also the GitHub. Right now, we also have not only use our own ANIT to predict energy and forces, we also use it directly in MD codes or Monte Carlo codes, or even with the genetic algorithm codes. For example, we have already implemented together with ASE, LAMS, Tinker, DL Poly. You can also look up, just submit it, publish it in the JCPs this year. So ANIT actually is widely used in many different type of high performance computing architectures and systems. So together with the main developers, Professor Urban at Columbia University, we already have been trying and test and run ANIT with many different HPC systems in the US, and also now we just access one allocations in the Dutch NW or SURF Selenium, which is really very high power. And not only show that ANIT can run really efficiently, we also implement and also develop further with many different features in ANIT. Together with April and Johannes, we developed the Taylor expansions, and also together with Dr. Molawitz and Michaels and Professor Markland and also Dr. Mori implemented ANIT LAMS. Just briefly to show you how highly parallels of our ANIT and also LAMS. This is to show the efficiencies. For example, this is the number of cores, and this is the percentage of the parallel efficiencies. you can see that in this case, this is one computer from Columbia University. This is just single CPU, like 12 cores. If we increase many number of core or nodes, its only loss efficiency is only 20%. Imagine here we run like 1 million atoms. It's take only 15 seconds. I think this is around 10 MD steps. But in realistic, in your simulation, you don't need million of atoms, right? Maybe a few thousand of atoms or 10K of atoms. So using the NIT together with MD code lamp, you can really run very long time MD simulations, for example. So just a quick showcase of neural network potentials for complex energy materials that I prepare. So we apply and use our NIT tools to show many different applications. For example, complex system, like looking at material with complex interfaces, amorphous phases, and also nanostructures. My own applications, for example, to understand the heterogeneous catalysis for energy conversions, and also for batteries material, looking at lithium transport in lithium-ion batteries, for example. So this is just to show the neural network potentials based on our own software package, and a few references that I already have shown here based on my own work. But of course, there are so many different research questions that can be really demonstrated or worked, and maybe it could be useful. So we also support NIT users, and already many others nice publications during the last few years. If you are interested in NIT, feel free to contact us. We have also the forums, and also really happy to help you to get started. So here, if we already have really good, efficient and accurate neural potentials, this can really use to do simulation for such a systems. This is back then when I was students with the Professor Bello group. So we try to investigate the copper zinc oxide catalyst, which is for methanol synthesis. So the system, really exhibits strong metal support interactions, and our experimental collaborators were looking for an explanations of their observation. For example, here, how can the copper grow in these shapes with different conditions? And you can see that with our neural potentials, with like 8,000 of atoms in these nanoparticles, or in this model that we just simulated, you can see that with our neural potentials, we cannot do this calculation with DFT. So this is just to demonstrate how we can use our efficient and accurate neural potentials to looking at such a system size. But one example that I would like to show you before we really move to the tutorials, I also would like to show that how complicated of amorphous lithium silicon. This is the silicon anode for lithium-ion batteries. So we train neural network potential to reproduce all of the lithium silicon ground state crystal structures, and also amorphous structures. Here on the left, you can see the phase diagram of a different lithium silicon alloys is showed, and then and potentials predict the same structures and energies as the FT. That's why I only show the FT results here in the figures. And on the right, the predicted voltage profiles from our calculations are also in good agreement with experiments, like you can see here. But our DFT calculation at the 0 Kelvin, but the experiment is really depending on the experimental conditions. In this case, this is 415 degrees Celsius, and in the blue one, it is at room temperatures. But actually, understanding lithium transport in amorphous silicon based on simulation really require large structural models because of the complicated amorphous phases here. I just show here, we also try to validate our neural potentials for lithium diffusion parts. As you can see here, the agreements between our neural potentials and DFT is excellent with many different parts, like you can see here, and also different compositions of lithium in the structures. When the battery is cycling, so lithium is insertion and also extraction, right? There are so many different compositions that can occur. And not only accurate energies, we also run long MD simulations, also comparisons of the energies at the beginnings and also at the end of the second nanosecond long MD simulations. So the potential energy surface or our end in potentials performed very well in MD simulations, like you can see here, and also many different compositions. And then we use the validated lithium silicon and in potentials, we simulate very long time simulations, like a 5 nanoseconds, and also very large nanoparticle, like a 12K atoms with the MD simulations. So you can see here very large nanoparticles on the top. And not only that, we also can use the same neural potentials to looking at the bulk structures with different compositions. And then we run MD simulation with many different temperatures so that we can really predict the diffusities using the linear plots and then estimate the conductivities at room temperatures. So not only that, we also can validate our results always with, for example, experimental measurements. You can see that our predictions of the diffusities is also in good agreement with many different experimental reference, like you can see here on the left. This is just only 2 examples that I would like to show. Currently, we also develop neural potentials for complex systems with our students and postdocs at Columbia. When I was in Columbia, that we also got funded from the US Department of Energy. So until next year, so we are developing neural potentials to describe complex lithium anodes and lithium cathodes here. And not only this, many different type of crystal structures, and during the battery cyclings, it's also become amorphous. And also Annika Stucker looking at the solid and liquid of the ethylene carbonate as a lithium anode. So there are so many different examples. So this is the overview of neural potentials that I would like to show you using ANET. But now we are going to looking at tutorials. So Venkat or Elena, how we are going to work? Shall I walk everyone to the deep notes I prepare and then let everybody use later?
I think at this point, maybe we could, if you don't mind, we can have some questions on the lecture and then, yeah, and then we can move to the tutorial.
Okay, yeah, exactly.
So,
this is a break. Maybe I
Federico,
talk very fast.
No, I think we are actually on time. Yeah, so that's very good. Yeah.
Questions for the theory side before we do practical?
I have a quick question if I can ask.
Yeah.
We already have 2 hands raised, actually.
Oh, sorry, I didn't see.
3. So I think the first was Ganesh. Would you like to ask your question?
Yes, I have 2 questions. My first question is when you say 500 datasets or 1,000 datasets you were using for fitting. My question is, it's refers to 500 step of MD run, right? If for clear.
Which part? I'm sorry.
I'm just asking when you using you are saying 500 datasets or 1,000 structures to fit your potential. So that means you are saying this exactly, yeah. The structures with when you say 500 structures or 1,000 structures, that means you are saying 500 MD step run. That's what you mean, right?
So this data set develop and also create from April. I believe that this is from both geometry optimization and also MD structures. And then we randomly selected only 500 DFT or the structures from her data set.
Yeah, the structures means like when you do MD run, 500 ionic steps. That's what you mean here, right?
I think it is the geometry optimization until you get the convert of the structure.
I think that the question is, this is the size of the training set, right?
Yes.
Yeah.
And was that derived from MD or some other way? So MD and geometry optimizations?
So we have also geometry optimization at the 0 Kelvin. We also include also some MD simulation of different frames. So there are two types of structures.
Okay, okay, I see now. Okay, so that means yeah, I got that point now. Okay, then the second question is how you are taking this cutoff radius for amorphous structure to fit?
Okay, this is very good questions. So the cutoff radius really depending on your materials. So we use 6 to 8 angstroms to capture our long range amorphous structures because it's really can be large system, right? So, yeah. In my because this is we have the condensed phases. It says 8 angstroms already capture the information that we need to understand or we need to learn in our lithium silicon structures already. But we combine many different region or many different compositions.
Maybe the follow-up question for this question, the problem is when you do a amorphous structure fit, then you try to run with MD, classical MD. Then if you are not including all the forces corresponds to the volume, or suppose I am trying to do melt and quench, then I fit the data sets which is not beyond the liquid stage. Then I try to run it in a liquid phase by fitting it in a solid phase. Then the calculation should crash, right?
So maybe I can explain a bit more. So if we have, for example, let's say this is like the amorphous structure, let's say. So we have include many different, you see my slides, right? Includes many different regions like a puzzles everywhere, like a 8 angstrom are cut, 8 angstrom are cut. And then we combine in one big data set. And then use the neural network potential to evaluate the parameters before we then use in the real larger simulations. So this means our cut off of 8 angstrom of different pieces of information, it will be included in my reference data set. So this means you have, like I showed at the beginning, that we have this data set. It should contain many different small structures in your training set, but each small structure should be different type of configuration included in your training set.
Yeah, that I think I got that. But my question was, when you suppose I'm adding the data sets to my training sets, like 500 Kelvin data sets from MD run, then I try to look at 1000 my real properties in 1000 Kelvin. So that doesn't work, right? It crashed. The calculation should crash.
Yeah, because of during MD simulation, some structures that you have is also can be very close to each other, which is including like a high energies. So you cannot use pure MD structure of the frame, each frame of your MD structure, including the training set. You need to introduce also the short distance, the high energy structure in the training set. Because while you are running MD simulation, at some point, your structure also will move very close to each other. And this is very important. So the repulsives, like, this, like here, in this region, the short distances, you need to have like you have to include this in the training sets too. Otherwise, it also cannot work. And sometimes like my simulation that I just show you, it also can explode. So it's also important to include very like a compressed structures in the training.
Thank you. I will discuss it later, maybe with you. Thank you for that.
Yeah, just go to the selection notes. Yeah.
Yeah, if you have like extended questions, especially relating to your own research projects, maybe it's better to ask them in the the poster sessions or the study rooms. So let's go on. I thought Victor had his hand raised, but it seems not anymore.
Yeah, my question was answered in the meanwhile. Thank you.
Okay, all right. So let's go on to Sean, and I think you were the next one.
Yes, let's briefly go to the tutorial that I prepared. So this is just what I'm going to show. This is the init, the flow, how to say, the framework or the flow chart that we have. So as I already mentioned before, we have like the input node, the hidden layers with training, and then the prediction that you can use it like energy of forces here. So the orange part is this how to change your atomic structures to describe the local environment. So we have, it is called in the tutorial we will have, it is called generate. Generate means convert your change the XYZ coordinate to some kind of like a fingerprint. So you will have two files, the generate.int and fingerprint. This is file to describe your each chemical species that you have. And then training or fittings by trying to find the best hyperparameters to optimize. Then we also provide different algorithms to evaluate your parameters, right? This is called train.in. And then for predictions or use it in application like an MD simulation, we also provide many different of modules can directly predict energies from your parameter that you have that fit, or can use it in application like in MD or MC code that we provide like in ASEs or in Tinker or in LAM. So you will see later in the short. So I also provide all of materials via GitHub links. You can also looking at here like a GitHub Atomistic Net and Psi-k MLIP workshop 2021. So you can download and everything. And the notebook here is it I just prepare, or we just prepare in the way that it can use for deep note, like we just here. So this is
I take the opportunity now to please remind all the participants to open Deep Note, since in order to follow the discussion about this tutorial.
very good. So I don't plan to run everything here because we already have the select channels, but I provide all of the Jupyter notebooks with really details and explain what does mean line by line, and also provide documents. And I would like to briefly show what Lily need to start from the beginnings until uses and applications. So we also provide some reference DFT calculations in the ANET format that you can really use and test for this workshop. And then also some parameters training and fittings by looking at like a change of few parameters that you can really modify and train by yourself. And then use it in the MD code we also implemented also in ASE code and ANET LAMs, right? So this is the deep note link, and I prepare also, if you see my deep note, I can see already many people looking at here. So do you see my share screen still?
Yes.
Okay, good. So I would say that today, I think the first one, this is just to install. I would like to just show really briefly to show what we really need. Again, if you have any questions and many other things is really happening here, you can contact our ANET team. Myself, I'm happy to discuss. Also ANET LAMs, Michael Shen, and also April also ready to help. And also Alex Urban also will be happy to help. This is the contact if you are interested in. So this first one, this is just install ANET. And I just prepared this. This is also my first time to use Deep Note. So maybe I cannot answer your questions very well on Deep Note, but I test, and also Venkat and Elena already have to test and run. Everything seemed to work well with this. So this is basically just install, and you just provide and import some like Cytons, and also just install the Cyton. And then we have already some of the link to download ANET and also to compile ANET. Like here, everything already done, and also show this is just how everything works. And then later, you can also import the ASE that we can link as use. I think maybe some of you already know how to use ASE. Then ANET also interface, like a Python and Python interface. with ASE and use it easily. Many different applications that you can use ASE to. And yeah, and this is what you can really prepare and to use. So basically, the first one, this is just to help to install, and that's it. And now, second one is use the init, mean like after you already construct very efficient and accurate potential energy surface or neural potentials already, if you want to use it in a really very nice and professional MD code, is it also linked with the LAMP. So in this one, we also write it down how to really compile init and LAMP interface. And again, if you are interested in and learn more about this, we can also discuss this later. I also compile already init LAMP for everybody so that you can really just use it. But the real tutorial for this workshop is this one, 03 init tutorial. If I have time, I would like to walk you all here that discuss the init tutorials, because of there are so many different things that it could raise many questions from the audience.
Yeah,
so,
I think we can do the third tutorial as a, yeah, I think we have enough time for that.
Okay, that's nice. Okay.
Yeah, we are good on time. Yeah.
Okay, good. Yep. Okay, the first one that I already showed. So again, Venkat, as I already discussed with you before, every block I already explained everything and also tell you what to do and how to do already. This is just basically just import libraries that you need to run. And then the first step, we have to, I call generate. Generate means you convert your XYZ coordinate to local atomic environment. So this it can then later we use as a reference information before we really train or fit our new network. So the example that I provide is the titanium dioxide. I also provide the XSF database in the folder that you already you can take a look and also check everything there. And the first one we use after compile init already, you will get the executable file is called generate.x. So the way that we are using, you can see here when the generate.x in the folder that we have, I call it this generate 01 generate because it's like a step one. So 01 means like a step one. You have to convert or transform your XYZ coordinate to local environment atomic structure that you have. And the file that we will have is the generate.in and also the fingerprint. In this case, because I want to show example of titanium dioxide. So we have the oxygen, the fingerprint, this is the setup of the fingerprint, and titanium dot fingerprint as a setup of the fingerprint. So after you run, you will get the output. It is called generate.out, and also the binary file is the titanium TiO2.train. So this is you cannot open because we make it like in the compressed, but we also have the script or front-end code to convert this to ASCII or to text, but not in this case. Please don't open TiO2.train. But the others file you can open via text. So this is explanations. If you have time, you can also read by yourself. But what I would like to show and explain what is in the generate.in. So this is just the command how to read. So I mentioned this is the in generate.in. We have like the output name. This is the after you convert your atomic structures XYZ coordinate. So you would like to have the local environment as a number that you would like to. Sometimes we also scale as a number like a -1 to +1, or it's depending on the, what you want. But I think init that we have, we scales of the local environment that we after we convert all atomic structures and also each atoms in the structures. I think it's from -1 to +1. And then the type in the chemical species that you have. In this tutorial, I show titanium dioxide. So two types, this is oxygen and this is the titanium. And then we provide, this is like a atomic energies. You could also have like an isolate oxygen atoms, or you can also have titanium dioxide, and then you divide it by number of atoms. So these numbers will be used to just part of to fit or to train. At the end, we will use it to add up or to subtract as a calculation of the cohesive energies or total energies later. So this is basically like a dummy or the constant. So many people ask me like, what is this atomic energies for oxygen? So usually sometimes we use like a O2 and then we divide it by 2. Or sometimes we just use oxygen atoms and then make the big box or isolate oxygen atoms and then put these energies there. So this is basically like just one single oxygen energies in the Phi. And titanium is also the same. And then the name that we would like to set up, like I just showed before, this is oxygen, the fingerprint, and also titanium at the fingerprint setup. And then Phis, in total here, in this case, I only selected only 528 structures, but in the full database of our titanium dioxide, we have around, I think, 7,000 structures. But for this tutorial, I only picked around 500 structures here. So this is the GenerateIn. So we just basically like list what we have. And now looking at the fingerprint setup for example, for oxygen atoms. So this is based on the Shepard descriptor. This is basically the input file that you have to describe your fingerprint setup. So basically, this is just the text. You start with describe or description and also end with this. This is just a note that you would like to know, just for you to remember what it is. And then we would like to describe the central atom is oxygen, and then the local environment, two types of species like titaniums or oxygens. And then armin, so we also try to ignore or exclude the atom that in the short distance, like a 0.75 angstrom, but you can also have shorter, maybe 0.4 or 0.5 angstrom. It's depending on how you want to play. And then we also have many different types of descriptors. But in this tutorial, I use our newly implemented Shepard polynomials. So this is the keyword. This is called Shepard. So basically, you just have just one line. For example, here, the radial cutoff just 5 angstroms, and number of the order of expansion that we want to have 12 order. And the angular, we also have just only 3 angstrom, and number of the order with just 5. So from my experience that the RDF or radial descriptors is more important than the angular descriptor, but you can also try. I mean, you can also play around because of the larger distance is also take more CPU time. I mean, this is just to for tutorials. In realistic, we use like a 6 to 8 angstroms. This is just to make it really fast and for everybody can really test and try. And then this is how to run. Just this is our executables, and then is it in serials, and then when we run, this is the generate.in, and then when we print it out, this is called generate.out, for example here, so and so. Yeah, sometimes if you have already filed this means it's already done, you can also remove if you would like to generate again, because of if you have it already, it will just use the old generate that you already did. And now, this is now, let's say we already have .train is already convert our atomic structures to local environments already ready. Now we can do the second step. I call 02 or 2 mean now training or fittings. We use neural networks. So looking at some files in this folder. So I usually do different folders to show different steps. Maybe it's easier to understand. That's why I make the second folder. It's just called 02 means step 2 to train. And usually we have, yeah, I also provide a good example because otherwise it will look really bad because of I make it very small hidden layer and also notes for the workshop. So basically we have the most important is called train.in. So in train.in, is contain information that you need to put, and the rest here is this from the after running already, and I already test run yesterday. That's why you have a lot of files. So the most important is that in this folder you need train.int and the local environment that we already generate from the previous folder 01 generate. So we need to call, or we need to link to tio2.train. Do you remember that? This is from the previous folder, the step 1 generate. And then we have to call. So let's take a look quickly on train.in. What do we have? So this is basically the train.in that you have. This is the local environment, or just say the reference data that we have from the 01 generate. Is it tio2.train? And then the percentage that we use it like we split 10% as a test set or for validation. So I use test percent because it just makes sure that it's not trained. Actually, this is validation set. So we only use 10%. And in this case, the how many iterations for the workshop here, I use only 100 iterations. And sometimes we also have really very bad or high energy structures in the training set that we just use it here. So we don't want it. We also make like, okay, we only include the structure maximum energy is like a minus 0.05 EV. And we also provide many different methods for minimize the parameters or many different algorithms. So in this workshop, we use BFGS because it is also efficient and fast. We also have many other, you can take a look later in init menu. And now the network, now we have to find ways to minimize, to optimize the hyperparameters. So we have the type of atoms. This is the titanium dioxide, and then write it down as titanium and 2 hidden layers, and each layer have 5 nodes. And I use T is a hyperbolic tangent as an activation function and 2 hidden layers here. So this is basically the information that you need to use to find your hyperparameters in train.in. And now, yeah, and then you get a lot of files that is produced here. And this is parameter that you need to use it always, parameters that you will use it in application is called .nn, so .nn. So let's take a look now how everything works. I already trained before. So it is around 100 iterations and everything run. And then we can analyze our training results. For example, looking at trained and test, like you just see here. But I forgot to show you the how to read. So we have many different information. Maybe take a look quickly on the head. This is we call. So epochs or iterations. And this is read the qualities of the neural network fittings, the training set. And this is the validation 10% that I already split from the previous train.in. So this is the mean absolute errors, and this is mean absolute for RMSEs. For example, this is for the train, and this is for the test. So basically, we should observe the information MAE or RMSE from the test to monitor how good progress of our neural network training. And then here that I show how good it is. And this is we just run 100 iterations. So you can see that our train going down and more. Typically, our trainings that we have a few thousand of iterations, but to make it quick, so I only make 100 iterations. And the test set here is this, the orange color. It seemed to be okay in this test. But again, note that this is very small network, only 5 nodes and 2 hidden layers. This is not yet good, but just to show and to demonstrate that everybody can run and test for today's workshop. So, and then I also prepare a good already in fit. This is like around 5,000 iterations. And you can see here, it's smooth and nicely, many different iterations from the same titanium dioxide set and around 7,000 structures that include from our init paper. You can see that already like a few I mean, both the trained and the test of, let's say, validations is always smooth and going down. But you can see that at the end, it will go really larger. So this means it's overfitting. So basically, I would say that we can select some iteration, maybe 1,000 iteration or 1,000 epoch for application already to use it. So we also check if we predict, for example, this is the DFT energies and this is neural network predictions. So both all of the validations, atomics, I mean, the structure that we have really have the very nicely predicted like 45 degrees. So it shows really good agreements between the neural network predict the FT energies of structures. And this is a init Python interface with the ASE code. So we also use it, some function from ASE, for example, to calculate many different informations. Okay, yeah, for example, here we have titanium dioxide, and then we also looking at a larger scale that we can also make supercells, and then we can run MD simulation, right? Yeah, or looking at the Python and ASE to predict like equation of states from the good neural network potential that I already prepared. And this is, I provide all of the equations that also the plot that you can easily apply and modify to your own research. Here, for example, here, use the good neural potential that I fit and share with you already. And this one, this is the x-axis, this is the volume of the titanium dioxide, and this is the energies. And neural networks fit really nicely compared with the DFT points that we also have that you can see here. And also use the later example, this is the init lamps. We already, we already comply in the 02 already, like you can see here. And we show as an example of water. I think I would like to show some how to, after we run and work on the tutorials, number 3 already. Let's take a look at some example. Do you see my slides here?
I think, Nong, we are almost reaching the end of time. Yeah. Yes. So, but thanks for showing us the tutorial. I'm sure this will be very helpful for people. Yeah. So just to let people know, I mean, if you're on DeepNote, you can duplicate this tutorial and you can run it yourself. And as I've tried this before, you can really train this potential in 5-10 minutes, and you can go through all the steps. You can also do it later on in your free time.
That's
and yeah, and if you have,
do we have time for one quick question?
Yes.
One quick question. Yes. If it's
just so basically all you need is these XSF files that have the geometry, and I'm guessing the energy of the DFT calculation somewhere in them. So in the format, you put the energy somewhere and just the geometry. Then you prepare 3 input files, right? The generate.in and the 2 fingerprints files, and that's it. And that makes the training data set, right?
Yeah, everything is provided. It will be possible for you to do the training yourself. Yeah, and
no, I was just asking conceptually. The energies of the DFT part, they enter the XSF files. That's where they enter.
Yeah,
that's right. So in the XSF files contain energies, XYZ coordinates, and also forces. Fx, Fy, Fc is also in the XSF files. So we have everything there. But before we really leave that, I think after we predict the reference data, we also need to validate our predictions from our prediction. For example, of course, compare with your accurate, the first principle data. And also don't forget to also compare your predictions from experimental data. And also one last thing that I would like to really discuss again, that's why we are here together, sharing the tools and also open tools and also share data is really will help and work together with communities. It really will help everybody to make the progress of the machine learning potentials communities faster or even better, that we can focus on to solve research, not only just sit down and develop the tools. This is my last word. Thank you very much, everyone.
I couldn't agree more.
A lot,
Thank you.
Thank you.
Yep.
That
See you
really
can I
next
echoes. Please go on, Max. Yeah.
Yeah, can I just, so I know a lot of you still had questions for the speakers. So there are a few options, since we don't have that much time between talks. Try getting in touch with the speakers over Slack, for instance, and ask if they're going to be around in one of the study rooms, right? Because we know the speakers are all busy. They might